Welcome. Patricia, for those who don't know, is a computer scientist, PhD candidate at the University of Toronto and a postgraduate affiliate at the Vector Institute, doing research on privacy-preserving natural language processing with a focus on applied cryptography. She also does research on computational methods for lost language decipherment. Patricia is the co-founder and CEO of Private AI, a Toronto and Berlin-based startup working on making privacy preservation and GDPR compliance simple and easy. Wow, that's huge. She's a recipient of the NSERC Postgraduate Scholarship, the RBC Graduate Fellowship, the Beatrice Trixie Worsley Graduate Scholarship in Computer Science, and the Ontario Graduate Scholarship. Just that? That's it, Patricia? So she has 8 years of research and software development experience, including at the McGill Language Development Lab, the University of Toronto's Computational Linguistics Lab, the University of Toronto's Department of Linguistics, and the Public Health Agency of Canada. She's also a member of the board of directors of the Equity Showcase and one of Canada's oldest not-for-profit charitable organizations. So Patricia, welcome back. Thank you so much for joining us again. And I'm really looking forward to this. So I'm going to get off screen and I'll let you get at it.
All right. Thanks, everyone. Thanks so much for coming. Going to share the screen. Okay, so I love answering questions. So if at any point you have questions, by all means, put them in the chat and we could talk about them. Much more interesting to have an interactive presentation. So this is a talk about privacy preserving machine learning. Why do we care about privacy preserving AI or machine learning in the first place? Pretty standard stuff, like there's a lot of useful information that you could capture from personally identifiable information or data that contains personally identifiable information. There's sensitive data that's at risk from either autocratic governments, from hackers, or from employees who may or may not be choosing very easy passwords, and from manipulative companies. And we, as engineers, really like having access to data, especially for machine learning models, so that we can make our stuff better. So another reason is because it's the right thing to do financially, to integrate privacy in AI. So if you look at the ever-growing fines for GDPR non-compliance, that is increasing, and it seems like in next year, those fines are going to skyrocket because there's a bit of a grace period that's kind of ending. And the European Union is also coming up with ways of really enforcing GDPR compliance more efficiently. Also, if you want people to use your stuff, a lot of the time, ensuring their privacy is a great way to make sure that there is no churn. So a lot of people are becoming much more aware of what is and is not okay to be done with their data. And people are becoming much more conscious about the kind of products that they use. One example is Signal, for instance, where you could see a spike in downloads right before the Black Lives Matter protests, once they integrated the image blurring feature in the app. So it automatically blurred faces, and then you could choose what else you wanted to blur with your finger. And you can see this across multiple different services, like DuckDuckGo. Whenever there's a scandal in Google for Google privacy, the use of DuckDuckGo goes up, for example. And there are also a lot of tasks that you may have heard of that use sensitive information. And this is definitely not an exhaustive list, but anything from genomic data, anything related to authorship recognition, natural language processing, automatic speech recognition, things like that, all contain sensitive information as input. So the 4 pillars of perfectly privacy-preserving machine learning And take the word perfectly with a grain of salt, because perfection is not achievable in reality, neither for privacy nor for security. But in a theoretical sense of perfection, this is what we would be looking at. So we'd be looking at training data privacy, so avoiding training data inference attacks about what kind of information was in the training data. So for instance, if somebody has a social security number in a piece of text, in a pile of text, you don't want your model to memorize that rare event. And then the outputs be used as a prediction, as a way to determine what the most likely outcome was in a character language model, for example, when they input certain digits. Then there's input data privacy, which very much like output data privacy is about preserving user privacy. So it's really about giving the user control over their information, also ensuring that that information doesn't get misused or even stored somewhere you don't know where it went, which can cause problems with the GDPR, which requires you to keep track of where data are stored and processed and how they're processed. And then there's model weights privacy, which is really about the bread and butter of the companies that are creating the model. So you both have to preserve the privacy and security of the model by ensuring that the weights are secret by encryption, for example, or by ensuring that they can't be reverse engineered based on the outputs. So in the wild, I'm gonna use some COVID-19 examples for how these different technologies can be used and under which circumstances they're the right ones to use. So this survey shows conflicting support for Canadians for COVID-19 tracing app. So what Canadians are worried about here are really the input and output data privacy. They don't really care about the model weights privacy, and this doesn't really require training data. Okay, so what are some approaches that you need? There's the standard cryptography, and for standard cryptography, there are pretty much two options. There's symmetric encryption, which allows you to encrypt a message with the same key that you'll use to decrypt it. And then there's asymmetric encryption, which has a public key for encrypting and a secret key for decrypting. And that tends to be much more efficient than symmetric encryption. Symmetric encryption tends to be much more efficient than asymmetric encryption. However, symmetric encryption isn't as practical because you can't just share the secret key. So the way that this is usually used in practice is you encrypt a symmetric encryption key using an asymmetric scheme, and then you send that over, and then the rest of the communication is done using symmetric encryption. Now more and more, homomorphic encryption is being used, and the way that homomorphic encryption works is specifically you could have a data owner that has an encryption key, encrypts two messages, sends it to a service provider encrypted. The service provider decrypts those messages, sends the encrypted result. The service provider computes on the encrypted message, sends the encrypted result to the data owner, and the data owner decrypts it. It's getting past my bedtime, so I apologize for stumbling. So the data owner decrypts it without the service provider ever being any the wiser of what kind of information was sent to the cloud. Okay, another option is using secure multi-party computation. And the idea behind secure multi-party computation is you'll have multiple people submit some information, and then the output is what's shared, but the information that's input is secret. So here's a very insecure example, not to be used in real life, but just to give you an idea of how it works. So some party one might send a message plus a random number to party two, who can add a message to that result and send it to party three, who has their own message, and party 4 adds their own message. And then party 1 can remove that random number, get the sum, and then disseminate it to all of the other parties. So this is often done using garbled circuits. I could explain that a bit more during question period if you're interested. Another option are secure enclaves. And secure enclaves are, for example, like Intel SGX chips, which are in your CPU, and anything going inside, if you have an Intel chip, usually in your CPU, and anything going inside a secure enclave is encrypted and then decrypted in the enclave, computed upon, and then anything going outside is encrypted as well. So for secure enclaves, not even your OS or kernel has access to the information within it. Okay, so those three solve input and output privacy to various levels. There's, in practice, lots of theoretical work on homomorphic encryption in machine learning. You could check out the IDASH competition for homomorphic encryption for specifically genomic data analysis. And there's also some new work being done in practice in industry of combining homomorphic encryption with machine learning for things like anti-money laundering. Then there's multiparty computation that's been being used for genomic diagnosis using the genomic data owned by different hospitals, for example. So you can check out this really awesome paper by Jagadish et al. To see something like that in practice. There's also a lot of talk about using MPC for voting systems, for example. So you may have heard it there. Then for secure enclaves, you've probably had some sort of interaction with an application that uses secure enclaves for either facial or fingerprint recognition. So for example, Microsoft for passwordless authentication uses secure enclave within their computers in order to ensure that you are who you say you are. And that's great for two reasons. One, it does preserve input privacy. So they can't really say who you are for wherever you log in, right? So there's that. But it also preserves the security of your fingerprint information from it getting accessed by a malicious party. So how do you compare these three and how do you decide which one to use? Oftentimes what you're doing is you're balancing risk with implementation and deployment complexity with computational complexity as well. So for homomorphic encryption and for secure multi-party computation, you can have quantum safe guarantees depending on the schemes that you're using, which what that means is specifically you're using, there's currently no algorithm that breaks these schemes using a quantum computer in polynomial time. However, that does not mean one cannot exist. Then an adversary, so for homomorphic encryption, secure multi-party computation, and secure enclaves, an adversary can still reverse engineer the model weights given the outputs. So one way of preventing that is by adding differentially private noise to the output of a model. However, I've only seen one paper in which that's actually worked out without affecting accuracy too much. In terms of implementation and deployment complexity, while secure enclaves have no mathematical guarantees of privacy possible, they are much easier to use than secure multi-party computation or homomorphic encryption. Specifically, secure multi-party computation can get quite tricky if you want to change an algorithm a lot, because you often have to recreate an entire circuit if you want to make a small change. And oftentimes, people think that homomorphic encryption is just generally not practical. It really depends on the use case. So in some cases, you don't need real-time results. In a lot of cases, you don't need real-time results, especially in healthcare and in genomic analysis, for example. where you're already used to waiting 3-4 days for even just a lab result to get transferred from one part of an organization to another. So it doesn't have to be 3-4 days for homomorphic encryption. It could get to 3, 4, or 4 orders of magnitude slower. And that's something that Microsoft showed for one of their implementations using a deep neural network. For a secure multi-party computation, the communication cost grows linearly, and the computational costs are approximately linear in the depth of the circuit. And secure enclaves are just lower than 1 order of magnitude if you don't go over the batch size for the enclave itself. Any thoughts on differential privacy? I've yet to hear a use case for that. Yes, that's actually the next part of the talk. So here's another concern: training data privacy, specifically NHS under fire for plans to store, track, and trace data for 20 years. So the problem there is in part training data privacy, in part input data privacy, but let's focus on the training data privacy aspect of it. So if you're storing it for a long time, clearly you want to do things with it, like probably train machine learning models to help you make future predictions. So the way differential privacy works is essentially you add some noise with some sort of mathematical guarantees in order to prevent identifying who is specifically in a data set, for example. So you can imagine querying a data set for how many people who smoke also have a rare disease. Then you get a result, which you add a little bit of noise. And if it's 3, if the result is 3, you have no idea if it was actually 2, 1, 0, or 6. But if the result is very large, you can make a generalization over a population. With only that little bit of noise added to it, it shouldn't affect whether or not that generalization is true. So smoking causes cancer, for example. You could see a huge amount of people that affects get 1 or 2 or 3 added to it, and that there's no problem there with that generalization. It's been also used for differentially private gradient descent. And there's this really great paper by Carlini et al. Called The Secret Share that shows how differential privacy can be integrated into a language model in order to preserve training data privacy. And the way that works is by doing differentially private gradient descent, which I assume most people have heard of by now. But the point of that is whenever you're learning, you don't want one record to affect a gradient too much. So you want to be able to generalize more, to better generalize, but not to memorize very specific information. So that's done in 2 ways. Adding differentially private noise to the direction of the vector. So you change the direction of the vector, and also changing the magnitude of the vector according to some bound. And so 2 techniques work really well, and in a lot of cases, they show that it actually makes the network generalize better to different scenarios because it isn't memorizing that very rare specific information. There's another option, which is private aggregation of teacher ensembles, or PATE, and that's by Papineau et al. And this one, so the way that this one works is that you've got the sensitive data that you want to use to label a student model. Let me go back. Okay. You have the sensitive data that you want to use to label this incomplete data and then train a student model. The way that it works is that you'd separate the sensitive data into n IID samples and then train a teacher model that's basically set up the same, initialize the same on each of these IID data sets, and you aggregate the results of these teachers with some new information to predict on. The results are aggregated, some differentially private noise is added to that, and then that is used to label the incomplete data and then train the student model. Any questions there? Okay. So yeah, essentially, you take the majority of the answers, and if it's not the case that the majority of these teacher models predicted the same answer, then you know it's something that's rare. And then that differentially private noise at the end adds that extra guarantee. Okay, so differential privacy preserves training data privacy. Then another option is anonymization or pseudonimization. And the way that anonymization or pseudonymization works is it removes, replaces, or aggregates personal identifiers. So aggregating is mainly done on structured data, removing and replacing often done on unstructured data. So replacing would be pseudonymization. There's a difference between personal identifiers like names, precise addresses, faces, and then quasi-identifiers like age and gender, which when combined together, it becomes exponentially more likely that you'll re-identify somebody. Okay. And what that does is it preserves training data privacy and to a certain extent, input data privacy as well. So that's something that you can't necessarily get with differential privacy for input data privacy, unless you're combining differential privacy with pseudonymization, for example. Another option is data synthesis, but I want to leave time for questions, so I'll just briefly mention it's possible to use GANs to synthesize structured data or unstructured data like faces, for example. Language is quite a bit trickier. And data synthesis preserves training data privacy. Often what you're doing is you're generating new data to train on in order to preserve in order to get access to more data. So in a lot of cases, you wouldn't be able to access the information if you didn't have the synthetic data to work with. So that was, if you think back about the problem about how long-term data storage is a concern, mainly because of training data privacy, because you could lock it away and do nothing with it and it wouldn't be that scary. But if you want to use it for things, what do you do with it? Okay, so in practice, differential privacy is used in Apple's QuickType prediction using randomized response, which I could get into in question period if you're interested. And it's also used in Google's Gboard in combination with federated learning and secure multiparty computation. There's also anonymization and pseudonymization that's used to de-identify clinical data sets. In my company, Private AI, what we do is we de-identify videos for sharing for training purposes, for example, or de-identify Slack messages from this company called Animo, where they are really central to their message is privacy, and they work in mental health, essentially giving predictions about how you're doing based on your Slack messages. So they de-identify Slack messages before their developers look at them. Then there's data synthesis, which Replica Analytics, a company based out of Ottawa, does some really great work to create synthetic structured healthcare data. And they do this also based on re-identification risk scores. I really want to leave time for questions, so I'll go over this if anybody has any questions about the differences between these. But in some, you can protect users' private data while continuing to use them for AI and machine learning in general. And you really need to have a clear understanding of which problem you're trying to solve before deciding on the method. So a lot of the times, people pit one method against the other. So differential privacy is better than homomorphic encryption, or anonymization sucks, we should use only differential privacy. And all of that is a baloney. It's different tools for different methods. And before you get that clear understanding, you won't understand which tool to use. And then also that there's plenty of room for research and innovation in privacy preserving AI, given the myriad of problems that there are in privacy and the huge amount of exploration we still need to do. At the University of Toronto, in Gerald Penn's lab, what we do is combine homomorphic encryption with natural language processing and spoken language processing. And at Private AI, we make it really easy to integrate de-identification within any process. So within apps, browser extensions, on-premise deployments, or private clouds. So for text, images, video, and audio. And I will leave you with this question of thermal imaging. So thermal imaging in particular is concerning and has not been brought up as a problem for privacy as much because you can't, as a human, really identify these faces very well, but a computer can, and it's actually facial recognition systems are actually more robust when using thermal imaging because it doesn't matter what the lighting is. The faces aren't as affected by shadows and a number of other reasons as well. So thank you. Thanks, David. Anyone have any questions? How do you know when the weights could be reverse engineered? Is it related to the size or complexity? Is there any good rule of thumb? That's a great question. So it depends what kind of information is being shared in the output. And there is no particular rule of thumb because that's still very much a research question. Ali, love the talk. Can you help us understand techniques that would protect the logic of the model from being reverse engineered, approximated post hoc? Thank you, Ali. Yeah, so I guess the number one thing is if you are deploying on the edge, for example, make sure you encrypt your models until they're running in RAM, for instance, or you could even make them run in things like a secure enclave. And the one technique I've heard for preventing reverse engineering of the model is adding differentially private noise to the outputs. And that is also very task dependent, but I'm happy to send you a paper that does this. Jordan, thank you, Jordan. Sounds like great properties to have. Why aren't we using encryption for everything? Is computation time the limiting factor? I know there are libraries like Crypton for PyTorch. Great question. So it's not just computational time the limiting factor. For homomorphic encryption, you do have limited, so you can only do polynomial computations on encrypted data. So anything that's non-polynomial, like ReLU, like sigmoid, you have to approximate. So there are certain approximations that you could do of these using polynomial functions. I could get more into that if you're interested. But essentially, there's a lot of research still to do to convert models for each of the tasks into the encrypted domain, especially in an efficient way. But one thing that's helping efficiency a lot for some companies is that they're converting a lot of their code bases to work with GPUs or FPGAs, and that can make things a lot faster for homomorphic encryption. Can you please talk about the real-world application of Pate? That's a great question, Satadal. I have no idea. I'll email Professor Paperno and ask. Let me know if you want the answer. Are there any papers on? I guess. Yeah, I guess if you have, for example, a data set with yeah, so if you have, for example, a data set with a bunch of information that you want to label for named entity recognition, for example, so people's emails, and you wanted to use this already labeled NER, that's definitely not a real world application. I'll email Professor Paperno and let you know, sorry. Are there any papers on Apple's QuickTime prediction or Google's Gboard privacy application? Yes, they're actually blog posts by Apple and Google. Happy to share those as well. Recently, pleasure, David. Recently, unreviewed work has come out about indistinguishability obfuscation by Jane et al. For non-cryptographers like me, could you explain what I/O is, if this is a topic you know about, or is it just hype? Yeah, I saw that article. I haven't looked too deeply into the methodology, but the idea behind indistinguishability obfuscation is you can obfuscate code and run it in a way that nobody could see what's happening in the code. No idea if it's just hype or not. So it would preserve model privacy in particular in a lot of cases. Any other questions? My pleasure, Jordan. Okay, well, I see we're past time, but if anybody has any questions, please feel free to email me. And if I promise to send you blog posts or answers to any of your questions, definitely poke me to remind me what your email is and where to send it to. Here's mine. Okay, really great to meet you all virtually.